let's try some more examples. Well, the first one is this one, the integral of 1 divided by x times the square root of x squared plus 4. So here, to to start the solution of this integral, the key point that you should identify is that this is an integral with a square root. So when you have the square root, we can use our table of inverse substitution. And when we are using the table, we should find the suitable category, right? Now in the previous two videos we did examples of the first category, but in here in this one we have it as x squared plus 4. In other words, it's like x squared plus 2 squared, right? So that falls under the second category. So the substitution will change, the angle is changed. See, here we are not considering the boundaries. It's kind of obvious why we are not choosing the boundaries, because at the boundaries tan theta will be equal to infinity, and the trigonometric identity will also be a different one, right? So that's the only difference, but the method is almost the same, right? So here we should start with our substitution of x equals 2 tan theta, right? And then we can see dx by d theta will be equal to 2 times sec squared theta, right? And that means dx can be written as 2 sec squared theta d theta, right? So now it's just a matter of substituting all these terms in the original integral. If I name this as I, then I will be equal to well, before writing the integral, I think it's easy if we simplify this expression first. So before writing the integral, if I write down the square root term along with our substitution, this one, let's see what will happen. Then it becomes 4 times tan squared theta plus 1, and from the trigonometric identity that I mentioned in the table, we have this relationship. So as I explained in the first video, we have the modulus of sec theta, but with the angle that we chose, it becomes just sec theta, because within this angle sec theta will be a positive value, as I explained in detail on our first video of this week. Then we can simply write our integral with this new simplification. So it will be equal to this integration. Now carefully you have to substitute the values appropriately, right? And then there will be some simplifications with numbers, right? So we will have 1 by 4 outside the integral, and this sec theta will be cancels out with one of the sec thetas in the numerator, right? And then what we can do is we can write we can write this sec theta and tan theta terms in terms of sine and cosine, which means sec theta is 1 over cos theta and tan theta is sine theta over cos theta. So this fraction inside the integral becomes sec, like you can rewrite it as sec theta times 1 over tan squared theta. So we just have to multiply these two things. In other words, our integral becomes integral will be equal to 1 over 4 times this one, because instead of this original sec theta and tan theta terms, we can rewrite it in terms of cos and sine. So it becomes cos theta over sine squared theta d theta. Now for this one also we don't have a direct result. So what we can do is we can use another simple substitution where we can substitute u as sine theta, right? So then we should so our target should be to convert our integral in terms of u. Okay, so here du by d theta will be equal to cos theta. That means du can be written as cos theta times d theta, right? That means now you can see this cos theta d theta term is already there in the numerator. So instead of this one, we can just write du. That means our integral will be equal to, for this one we can just write du, and in the denominator we will get u squared. And you can for this one we can find the answer by our standard results, right, which is equal to negative 1 over 4 times 1 over u, right? Because you can rewrite 1 over u squared as negative 2 du, so it will be equal to u negative 2 plus 1 divided by negative 2 plus 1, right, which is this. And yes, so now we have found the answer in terms of u, right? But see, we have two substitutions in the middle. Now we started with x, and because of this square root thing, we converted everything in terms of theta, but then again we were unable to find, although it simplified a little bit, we were unable to find an exact answer for this integral. And to integrate this one, we once again convert everything into u, right? So we have the answer for the given original integral, which is in terms of x, and we have the answer in terms of u. Okay, so first we should convert it in terms of theta, and then we should convert it to the terms of x. Converting into terms of theta is not difficult at all, because we know the value of u, which is equal to sine theta. So for this one we can just write it as negative 1 over 4 times 1 over sine theta, right? And also you should not forget to have the arbitrary constant throughout. And then when you have the answer in terms of sine thetas, how are we going to convert it back into the terms of x? We make use of the initial substitution along with the right angled triangle. Now the initial substitution was x is equal to 2 tan theta. In other words, tan theta was equal to x divided by 2. Now if we have a right angled triangle and if we have theta like this, and if this is the right angle, tan theta will be the opposite side divided by the adjacent side. And here to find sin theta we need opposite divided by the hypotenuse, right? So this is equal to sin theta, and 1 over sin theta will be the reciprocal of this one. Anyway, we have to find the hypotenuse of this right angled triangle, which is equal to x squared plus 2 squared, right? So that means we can rewrite this expression in terms of in terms of x as negative 1 over 4 stays the same, and for this one we can write hypotenuse divided by the opposite side, which is equal to x squared plus 4, which is the hypotenuse, divided by x, which give you the opposite side. And also don't forget to have this arbitrary constant. So this will be our final answer for the given integral. Okay, right. Now as a summary, if we see what we did, we had the integral as with the square root, and since you have a suitable format from the table, we used the appropriate substitution, and then we had an answer in terms of theta, but in the middle we had to do another quick substitution. Anyway, we got the answer in terms of theta, and to convert everything back into the original variables, which is a must you have to do, to convert it we make use of this right angled triangle along with these trigonometric relationships, right? Okay, and in the next video we will see how to do this second part. Now see, even in here it has almost the same nature, right? See, here you have a square root of the same type, so it's natural to use this calculation or this substitution, right? Okay, we'll see, but there's something else that we can also do, and we'll see it in the next video.